Here's the analysis of that thermodynamics of a hand warmer lab. First of all, we've got a data table, and your numbers might be similar. Maybe sometimes they're a little bit different, but I will use this sample data to run some analysis calculations. Now, we all probably have about 45 milliliters of tap water that we put in a styrofoam cup. The density of water is 1 gram per milliliter, so the mass should be about 45 grams. We were supposed to use 5 grams of each solid salt. Again, you might have 5.01 or something similar, so you can do the calculations with whatever mass you measured. We have the initial temperature of the water. We added the solids, stirred them around until they were completely dissolved, and then recorded the final temperature. Now, technically, when you do temperature change, it's final minus initial. So the ammonium chloride and the sodium acetate should have shown negative temperature changes in the water. When we do thermo calculations, we're often kind of concerned with the direction of the energy flow. So I want to know, is the temperature increasing by 7 degrees or is it decreasing by 7 degrees? So we got to put in that negative if the temperature is going down. In the middle, the calcium chloride should have had a positive temperature change. The temperature of the water went up by maybe almost 10 degrees. Now, the second part of the data section just wanted you to sketch a generic graph. And so with the ammonium chloride, the temperature went down. So maybe, I don't know, something that looks like this. The sodium acetate also showed a decrease in temperature, maybe not by quite as much. And then the calcium chloride would have increased in temperature, maybe something like this. And again, they're really generic, just general graphs. There was a free response question on an AP test not all that long ago, and they started them off with a graph of temperature change, and it was really similar. They were dissolving a compound in water and recording the temperature change. Well, that was the first part of the free response. Part A said, what is the temperature change? And so we had to know delta T is temperature final minus temperature initial. So they did have to make sure that if the temperature went down, they showed it as a negative temperature change. And the other thing that they had to do was measure properly off the graph. So if there were like little increments or markings on the graph, they had to make sure that they made a proper measurement. So they get to measure 1 decimal spot beyond the markings of the measuring tool. So if the graph had temperature marked like every 1 degree Celsius, they had to make sure that they measured with 1 estimate or 1 decimal spot. So they had to make a proper measurement off the graph, and then they had to do temperature final minus initial. And if it was negative, which this one was, they had to make sure that they included the sign of the delta T. Okay, label the final and initial temperatures. I don't care if there's a label in there. We're just looking for the general shape. All right, on to the good stuff. Some calculations. And number 1, we want to calculate the change in energy, Q, for the water as each salt was added. Okay, so we're going to do the same calculation 3 times. In the equation packet, Q equals MC delta T. So let's do the ammonium chloride first. Q is M the mass. Now here's where we have to be a little bit careful. In the lecture guide, we were doing a couple practice problems where we had maybe the combination of 2 solutions, and you had to use like the final combined mass. So if you mixed 50 milliliters of one and 50 milliliters of another solution, the final combined mass was like 100 milliliters or 100 grams. Well, similar here. When we dissolve these solids in water, the solid becomes part of the final solution. So we want this mass to be the final combined mass of everything that is now part of the solution. So it's going to be the 5 grams of solid plus the 45 grams of water, which in the end is super easy. This should end up being about 50 grams total. So where do I get that 50 grams? 5 grams of solid plus 45 grams of water. The combined mass, which really means that they should all be the same mass. I mean, unless by chance you didn't measure exactly 5 grams in one trial. Specific heat. Usually they'll specify a specific heat kind of right in the problem. We are using water as our solvent, and by far water is the most abundant particle in the solution. We're safe using 4.18 joules per gram degree Celsius, which would be the specific heat of water. Now you can look it up on a chart in the lecture guide. Often they just give it to you right in the problem. I think they might mention it in the introduction. And then finally, delta T. So for the first one, I would say negative 7.5 degrees Celsius. I plug it all in, and Q is about negative, oh brother, how far do we want to go here with our sig figs? Well, I guess that temperature technically only has 2 sig figs, so we could go 50 times 4.18 times 7.5. I suppose we could round this a little bit and say negative 1,600 joules. And I'm just rounding it for sig figs based on that temperature. There's only 2 sig figs, so we'll go with it. Then I move on. Calcium chloride. Q equals same mass, 50 grams, same specific heat, 4.18 joules per gram degree Celsius, and my temperature change was a positive 9.8 degrees. Again, yours might be a little bit different, so feel free to pause this video at any time and plug in your numbers. 4.18 times 50 grams times 9.8 degree temperature change. I'm going to leave this as, ooh, interesting. Okay, so negative, oh, this one's kind of funky. So really it's like negative 2,000 joules. Now if I wanted to get picky, I'm still going 2 sig figs. I might have to say like negative 2.0 times 10 to the 3rd joules, just to be specific, and make sure that I'm showing that 2 of those sig figs are significant. Ooh, that was a fun one. All right, and the last one is the sodium acetate, C2H3O2. Q, 50 grams, 4.18 joules per gram degree Celsius, and my temperature change was, I think, what, negative 3.4 degrees? If I remember right, yep, negative 3.4. Okay, negative 3.4 degrees Celsius. 50 times 4.18 times negative 3.4. I get a negative, like 710 joules. Oh, whoopsies, why did I put negatives in the middle? Hello, positives. Were you wondering if I was going to get to that? Hello, that's positive. Okay, speaking of positives and negatives, so we're getting this energy change. This energy change is in reference to the water. What was the particle that was touching the temperature probe? Mostly water molecules. By far the most abundant particle in that styrofoam cup was the water. So when the water temperature went up in the middle, it must have meant that dissolving the calcium chloride released heat. It's endothermic for the water, endothermic for the water. Well, it must have meant then that the calcium chloride dissolving released energy. It caused the water temperature to go up. If your Q is negative, it's exothermic for the water. So the ammonium chloride and the sodium acetate, exothermic for the water. So the water was releasing its energy, which must have meant then that the dissolving process for the ammonium chloride and the sodium acetate was endothermic. Dissolving ammonium chloride sucked energy from the surrounding water, so the water temperature went down. Well, why do we care? Well, for number 2. Number 2 now says to calculate the heat of solution for the dissolution of each salt. Now, delta H, SOLN, means heat of solution. This is the energy change for the dissolving process. So now we're going to calculate an energy change in reference to the dissolving reaction of the salts. Well, notice now that they want this in units of kilojoules per mole. Oh. Well, first thing I got to do then is calculate moles. I mean, I can easily switch joules to kilojoules, but I got to get these out of grams into moles. So, for example, if I used 5 grams of that ammonium chloride, I got to get her out of grams and into moles. 1 mole has the mass on my periodic table, 53.5-ish grams. Nitrogen plus 4 hydrogen plus a chlorine. All right, so plug that in. I guess technically now my masses are 3 sig figs, so maybe I'll leave 0.0935 moles. Okay, so I'm going to do that with each one. So I've got 5 grams of the calcium chloride. I need it out of grams and into moles. 1 mole has the mass on my periodic table. Now, one thing that I should mention, the calcium chloride that I used was actually a hydrate. Now, I think we talked about hydrates, oh gosh, like back in maybe even September. I used calcium chloride dihydrate. Now, it's not a big deal. It's just that there's a little bit of water in the crystal structure. But when I find the mass, it needs to be the mass of the calcium, the chlorine, and the water. So with the water combined, the mass is about 147.02. So if you're freaking out because you're like, wait a second, if I add calcium plus the chlorine, that's not the mass that I calculate. Yeah, it's just because the hydrate would include a little bit of water. So we'll include that in our molar mass. So we'll take our mass, 5-ish grams, divide by 147.02. And about 0.03, I'll say 40 moles. And yours are going to be really similar. The only thing that might be a little bit different is maybe by chance you had a little different mass. And then finally, 5 grams of sodium acetate, H3O2. I need her out of grams and into moles. 1 mole has the mass on my periodic table. But again, it was a hydrate. So it was really sodium acetate. It was a trihydrate, 3 waters. Not that it's a big deal, but when I find the mass, I have to include the mass of those waters. So we're going to use 136.08. Plug that in my calculator. 5 divided by 136.08.0367 moles. And so for the most part, I'm guessing we'll be all pretty similar. Okay, so now kilojoules per mole. So I want to go back to my answers from number 1, turn them into kilojoules. I also need to flip the sign. So these were all in reference to the water. So for example, the water temperature went down for the ammonium chloride. The water released 1,600 joules. Where did it go? It should have been absorbed by the ammonium chloride in the solution process. So number 1, I'm going to change it to kilojoules. So I'm going to make this 1.6 kilojoules. And I got to flip the sign. This is in reference to the dissolving of each salt. So again, when the water temperature went down, the water was losing energy. It was absorbed into the ammonium chloride, which we'll talk about a little more in a moment. Now I go kilojoules per mole. 0.0935 moles. All right, let's see what we get. 1.6 divided by 0.0935. All right, I might say something like positive 17 point. No, I might just leave it at 17. If I only go 2 sig figs, I guess. And that would now be kilojoules per mole. Sometimes they call it the molar heat of solution. It's a constant. It's a number that you should be able to look up on a chart. So with my data, it looks like dissolving ammonium chloride absorbs 17 kilojoules per mole. Oh, all right. We keep going. So the calcium chloride, the water temperature went up. So the water was absorbing about 2,000 joules of heat. Well, it must mean then that the dissolving process was exothermic. So I'm going to change this to kilojoules and flip the sign in reference to the dissolving process. So now this is going to become negative 2 kilojoules divided by my moles. 340 moles. Plug her in, divided by 0.034 moles, and I'd be looking at about negative 59 kilojoules per mole. So the dissolving of the calcium chloride was exothermic. I think this is the hardest part of the thermal unit. Okay, if the dissolving of calcium chloride released energy, that's why the water temperature went up. Oh. Okay, and finally the last one. For the sodium acetate, I'm going to switch this to kilojoules, so we'll say about 0.71 kilojoules. 0.71 kilojoules divided by my moles. 0.0367 moles. Again, you can put the positive sign in there. If you don't write a positive, we assume that you mean for the process to be endothermic. The water temperature went down by about 3.4 degrees. So the water lost heat. Well, it must have then been absorbed by the sodium acetate. Dissolving sodium acetate had a net input of energy from its surroundings. Got the energy from the surrounding water. 0.71 divided by 0.0367. And I'd be looking at maybe like 19 kilojoules per mole. Endothermic by 19 kilojoules per mole.